is, I don't know where it belongs to. Where it belongs, it may belong to number theory in some sense, it may belong to combinatorics, it may belong to group theory. It's somewhere in between. I very much hope it belongs to mathematics. Okay, so let's start in medias res, so in the middle. So let's introduce this notation. G star of n will be the number of groups of order at most n. Not exactly n, at most n. And the theorem I proved roughly 20 years ago is G star of n is n to the 2 over 27 times log square n, apart from here a little of 1 term. So this goes to, when n goes to infinity, this just goes to nothing. So that somehow may explain my abstract. That, okay, you sort of do expect to find some expression if you ask this question as an answer. What you don't really expect is that 2 over 27 will be the constant which really tells you the answer. Okay? This is, the point is that it's surprising, as I wrote here, so as I would remember, forget, that it's surprising that there is such an estimate. It would not be very surprising to have an estimate, okay, more than 1 over 100 and less than 200. But to have to pin it down, and I'm not trying to praise myself, the point is that it's funny that it exists. Okay. Yeah. Why is it interesting? So there are some amusing answers to this kind of questions. Like, if you don't know them, count them. So if you have any kind of structure that you're interested in, and you want to test whether you really know these guys in some broad sense, try to count them. And if you cannot, then you're missing some information. And maybe if you try to count them, whether they are graphs or groups or quasi-groups or standard systems, you may learn something when you do it. And these kind of questions are very easy to ask because you can ask them very simply. Okay, I have my favorite structure, how many are there? Very dumb question, but sometimes the answer is nice. And why is it interesting? In a sense like the four-color theorem. You know the four-color theorem, I guess. So the four-color theorem, in some sense it's completely uninteresting. I mean, the answer is uninteresting. Cartographers don't use it, mathematicians don't build any theories on it, but on the way to proving it, a lot of mathematics has evolved. So it's like, yeah, so there are these kind of questions which are in some sense simple to state, but the mathematics that comes up while you are trying to solve may lead to something more interesting. And I will try to give something that in some sense, how to say, in the end of this talk I will tell you something about random generation, which probably has more applications than this particular result. But there is maybe a third answer. I think it was asked by Hillary why he went up. But he said, well, it was there. So you have to try it. So I started in the middle, and the history or the genealogy of the problem is something. So why did I use G star of n for the number to denote the number of groups of order at most n? The point is I wanted an elegant result. It's very natural to consider the number of groups of order exactly n. But for this function, you cannot expect a result like that. Any hints why? Any ideas why? Mickey Albert is telling me that he's always asking such nasty questions from the audience. So, okay. But I don't mean, okay, so when n is a prime, when you have just one group. So, I mean, it's a chunky function. So it's rather, if you want an elegant result, it's better ask at most. And that's what, okay, mathematicians like to tell that their subject is so and so old. So let's go back to Mulder, of the Jordan Mulder fame, I believe, 1895, who determined the number of groups of square free order. So exact enumeration, and there are some ugly expressions in it, and you can read the definitions here, but it doesn't matter. The point is that depending on primes and stuff like that with this number, you have an exact expression. And there's a little bit more in this direction, like I think there is a similar expression for the number of groups of order n where all CeLO subgroups or P subgroups are cyclic. But basically that's it. And in some sense, in the paper that I wrote long ago about this, there is even some sense of proof that you cannot expect anything nice. So there's a weird constructions of many groups which uses deep number theory that I didn't invent. I was just using it, which disproves some optimistic conjecture. So it's not an explicit proof, but in general you don't expect an expression like that. Okay. You may have heard of Paul-Erdős. Okay, good. In other words, yeah. So so when I was a bit younger, like 20 something, and he was 70ish, I was one of the people whom he regularly called, like 6 o'clock in the morning on Saturdays, until he realized it's not the right time. But yeah, we had a lot of chats, and he was sort of interested in chatting about this as well, but he told me that this kind of topic was illegal in the 50s. You didn't count groups. The point is that he was also, among other things, a number theorist. And he has an ancient paper, maybe with someone else, sorry, I should have remembered, where they give a very precise expression for the number of abelian groups of order n. This is a number theory question. And maybe that's one of the first such papers, and there are a lot more papers, remainder terms, second remainder terms, third. It's a different branch of mathematics. But that's also something that people wrote on, and that's why he was interested in counting groups, but people didn't talk about it. But they did talk about it in the 60s. So the two results, a lower bound was given by Hickman, and then upper bound, which is quite tricky, was given in the thesis, PhD thesis of Sims. So this basically said the number of groups of order exactly p to the alpha, p prime, is p to the 2 over 27, here's this magic number, plus little o1 times alpha cube. Now how does this relate? When p equals 2, then p to the alpha cube is n to the log square n. So it's the same thing, but the cube becomes a square with this slight cheating. So really, it was Sims who came up with a proof. And long ago I had a chat with him, and he said that he was intrigued by this 2 over 27. So, and in some sense this is his proof. The thing I could do is extend this from time per hours to arbitrary numbers. Okay? Okay. There was another guy, an Oxford professor, who had many students and himself working on this problem. What?
Sorry, these are G's, so this is the exact number? Or
this is the exact number, that's why I asked why is G.
Okay.
So when you have square free numbers or prime powers, then you can estimate it. But as I explained, when you don't have such preconceptions about the prime structure, you can't. Okay, yeah, it's the exact number. Okay, so it was Peter Neumann who proved that the number of groups of order n is at most n to the constant times log square n. Okay, that is, it was in 1969 when the classification of finite simple groups was not even announced. Have you been introduced to this kind of thing? You may have heard of this a little bit. Probably not the proof. So basically what he proved is that this estimate holds if a similar estimate holds for the number of simple groups of order n. And by this classification theorem, there are at most two simple groups of the same order. Which implies that, okay, this theorem holds with something like c equals 1. The problem is that without the classification theorem, I really tried a little bit, other people tried, I think I can only prove that there are at most something like 2 to the n simple groups of order at most n, whereas the truth is 2. So, but maybe somebody can find an argument, so it may be it would be really, actually even this very dark 2 to the n bound has been put into a book because it has some application. So if anyone has some clever idea, I would just love to hear that. Okay. Okay, something about this classification, because I was told that it's better to tell you something interesting tales. So it was announced in 1983 and completed in 2004. You may not heard, so the story is that it was announced and then there was an 800-page manuscript by a guy called Mason that was responsible for one part. And somehow Mason was still realized that there are some methods which may be better of finishing this subproblem. And he just didn't finish his manuscript. Okay, these guys will do it or something. I mean, 800 pages, that's a long something. And then and somehow it never appeared. And I was a postdoc at Dynex, Rutgers University, where Borenstein was the director. Borenstein was the one who was really the director of this classification effort. And so people were bothering him and everybody, like the fields methodist there, that it's unfinished. So why is it unfinished? Okay, so Michael Aschbacher went on and okay, he said, let's look at this damn manuscript. And he found that it doesn't even claim to finish things. And there was he finished the whole with a 50-page manuscript. So I was present where he gave a talk on it, and then people asked him, okay, what about the rest? Did you check it? And he said, well, the methods are sufficient. Okay, that would do for the time being, and then people started bothering him. Actually, Borenstein, who was a very nice guy, died during that year. Everybody expected him to push other people, so a few years later, Aschbacher probably said that I have to do it. So Aschbacher and Steve Smith started working maybe 98 on this problem, and in 6 years they managed to produce a 2-volume, 1,200-page, not a paper, but 2 books, which finishes this thing called a quasi-thin case. And I have just looked at a review of that by one of the experts, and it says the first volume is a lovely exposition of the techniques. The second is I recommend only for the bravest souls. I could only read 1/5 of it, but a team of experts went through it. So anyway, but one can believe. So it's nobody can read it. Maybe if 5 clever guys sit together, they can go through it. Well, but still, it's finished. Everybody now expects that it's finished. even though, but then there are efforts to simplify this, but I will not talk about it. I think this is enough now. But you, but I think even with this example of counting groups, I explain counting simple groups. So the point is that if you don't use the classification or something like that, you get nowhere. It's true for awful lot of questions in finite group theory. If you use that, then you get very nice, precise results. So, okay, so about the proof, not of the classification, but my proof. So, so there's an obvious idea to use induction. There's this wonderful drawing here. You take a group of order n, you take a minimal normal subgroup n, which will be elementary, abelian, or a product of isomorphic, non-abelian simple groups. Not many choices for that, using the classification. And then you factor out. So by induction, there are not too many choices for the quotient, and you just have to put them together, and that's it. Yeah, so this thing about putting the top part and the bottom part together, this has, it belongs to a group extension theory, and the estimates are not very strong. So there are actually many ways of putting the bottom and the top part together, and also you have to do this induction in many steps potentially. So the point is that these not too small terms add up, and eventually they become too large. This becomes the main term of the expression, and that's a problem. So you cannot use induction, and I very cleverly really exploited what can be known about all these extensions, and he estimated the constant by 1/6 instead of 2/27. It's a very nice, very clever idea, but it's in some sense shows that induction doesn't give you what you want. So what can you do? Luckily, once upon a time I was a little bit more diligent, so I at least tried to read a little bit about the classification. So there is a 300-page fairy tale by Gorenstein about the 10,000-page proof, and it has a 50-page summary kind of thing, and that at least I read more carefully. And there is an important notion there, which I will not define because that would be frightening. But it's something you can find in any book now. It's so-called the generalized fitting subgroup, whatever it is. Fitting subgroup is in a soluble group the maximal unique nilpotent normal subgroup, and it has an appropriate generalization. The point is that there is a nice characteristic subgroup in the group, which, okay, maybe a lovely drawing, tiny. I think, yeah, I did. Yeah. So you have a finite group G, and it has sitting in it this group F star, and it has a very nice property. In group theoretic terms, the property is that any element G, which centralizes all of F star of G, is sitting inside F star of G. And this really means, forgetting this technicality, that F star of G is a, so the top part is acting on the bottom part as automorphisms. So there are not many possibilities. So my strategy is that when I was browsing through this 50-page summary of the classification, it hit me that, okay, if you want to avoid induction, okay, do it. So there are not many possibilities of F star of G. This is a little bit harder to prove than proving that there are not many possibilities for minimal normal subgroup, but not that too much harder. And then you can use various tricky things to show that the possibilities for this this top part that's not too much. And then you have to still put them together. And there are still these not so good estimates for extensions, the ways of putting together, but you have to pay this price only once. And that actually does work. Okay? So the enemy is induction. So it was nice to be, that was the philosophy. Okay, after that I had to work on it for a year or so, but that was the main point, avoid induction somehow. So all this, so this is a hint, and it somehow shows that it all leads to counting permutation groups with certain restrictions. And I will now go to this topic, so in some sense I'm leaving. That was the starting idea. Yeah. So I would like to talk about more generally about permutation groups. Okay, so you can forget about anything about G star or whatever. So there's a nice, well-developed, let's say, asymptotic theory of permutation groups. There is a non-asymptotic theory. For example, the most classical question about permutation groups, what are doubly transitive groups? Doubly transitive means that any pair can be brought into any other. Transitive means that you probably know that, yeah? That every element can be brought by a group element to every other element. Okay, these are nice, but they don't have much structure. So there are too many of them. But doubly transitive, the investigation goes back to Jordan. So is that any pair can be brought into any other pair. And these have been described explicitly as a consequence of the classification. An awful lot of work was done on that before, and the results in that went into this classification effort, but it was only after the classification that this particular project was finished. So that's again something, in particular it tells you that if you have 6 transitive groups, any 6 couple can be, then it must be the symmetrical alternating group. Nobody knows how to prove that. Actually, some people do model theory, like Hrushevsky, are daydreaming about at least proving something like that. And they have ideas, but actually they had these ideas 20 years ago. So, but maybe they will do it one day. Okay. But this is not a topic I suggest you to work on. Well, if you do it, I will. Okay. So let's go back to something simpler. So Peter Palfy, the present director of the Renyi Institute, you may know, has a theorem, the Palfy-Wolff theorem. Actually, again, something about mathematics. So he had this theorem, and I discovered somewhere in the library that a guy called Wolff proved the same thing, and then he rushed into the library and checked that they did it basically the same time. So nobody was first. So that's the way it's a joint theorem. So the theorem is the following. You take a subgroup of the symmetry group, degree n, and you assume that it has 2 properties. One is that it's soluble. Okay, no non-abelian simple groups anywhere. And that it's primitive. Yeah, you know this notion, primitive? So one definition is that the point stabilizer, it's transitive, and the point stabilizers are maximal subgroups. There are other more ugly definitions, but I prefer that. So the point is that these guys are very small, polynomial size. Actually, you can say that they have size that is n to the constant, where c equals 3.243. There is an expression, which I tend to forget, but it's basically, it's a precise constant. But the point is they are small. Okay, I was told to tell you many details. So one thing, why is this sort of useful, this kind of thing? There's a problem called the graph isomorphism problem. You have two n-vertex graphs. Try to determine by a fast algorithm whether they are isomorphic. Fast would mean, for mathematicians, polynomial time. Now this has not been solved, but group theoretic techniques using these kind of results have at least proved that if you have a bound of the degrees of the graphs, then there is a polynomial. So the most difficult graph, if you have three regular graphs, whether they are isomorphic or degree at most 3. So that's due to G. Lux, and he's actually using group theoretic techniques and ideas like that. So that's how this surfaced in the work of Pyber. Okay, so, and there is an unsolved problem there. The expectation that it may be polynomial, the algorithm, I think the best result is entity squared of n, or something like that. But it's not too clear. So, László invented the notion of moderately exponential for this kind of thing. The point is you want to tell other computer scientists that you have done something. Okay, so so this is true for primitive soluble groups. Primitive groups, in another sense, are important because they are the building blocks of permutation groups. If you try to understand them, then certain questions do reduce to primitive groups. And primitive groups actually do have a structure which is very useful, but on the other hand, if you don't have the classification theorem, it's completely useless. So, so that's a central notion in permutation group theory for this reason. Okay, but when I was working on this topic, this group enumeration, there was a certain lemma I just couldn't prove. So I gave a homework to Pyber. I asked him the question, is it true that the same kind of guys, primitive, soluble, and maximal among these, is it true that there are only few of them? I really needed that kind of result, and a day or two later, he just neatly described a proof of this, a one-page proof, based on some theory that was known to him. So it appears in my paper as an attribution to him. So it's not a joint work, he proved just this lemma's homework. But I really needed that. So this homework lemma, so again it says that the number of primitive soluble maximal subgroups, it's getting more technical, too many words. Fact is, yeah, that's the right name. There are only few. Few meaning polynomially many in n. Up to permutation isomorphism. So if you if you have two permutation groups, they may look different, but by permutation of the basis set, they become the same. So that's when I say the permutation groups are the same, it's not up to isomorphism, but permutation equivalence. So, oh yeah, there are more details on it in a book that I was actually very pleased that people wrote. So, it's enumeration of finite groups. There is a chapter of 100 pages which says, the title is Pyber's theorem. Interestingly, it never states my actual theorem, but it does a very good job explaining the background. So for all this stuff, there is a graduate level introduction. So basically, Peter Neumann was an Oxford professor working on this problem, and these guys are, some Indian names are longer than you expect, were his students. So they sat down, and eventually I wrote the book, which is, they saved me from this, which I wouldn't have taken. The point in this book is not the actual result, this 2 over 27, but the point is that it it really explains the background results, which may have other applications. Okay. But this homework of Buffy has, so the point is that the whole messy proof I had has no applications maybe, but this particular little homework lemma does lead to a new direction. That's typical. It's not the main part of a proof, but something tiny there. So, a corollary of this homework that looks again maybe ugly, I don't know, I like it, that again, now you count, too many words, primitive soluble groups, but you assume that they are degenerated, let's say two-generated. Generate the number of generators, you know, this notion maybe that that there are D elements such that any element can be written as some expression of these D elements. That's one definition. So the number of degenerated primitive soluble groups is small, polynomial. So this is a very easy consequence of this original multiple theorem and this homework. Okay, and again you can ask, especially after 35 minutes, so why is this interesting? I tried to explain. Give an answer at least. But I need another piece of notation. So people have this hobby of counting groups, subgroups. So for example, there's a big topic that if you take your favorite infinite group, finitely generated, and take your index and subgroups. So this will give you a function, fn. Okay, what does this function tell you about the group and what this can be? So this is some kind of a branch of between finite and infinite group theory. So one particular function is the number of maximal subgroups of index n. Index of a subgroup is the number of cosets of this subgroup. The percentage of that it covers of the group is 1 over the index. Okay. So so there is this corollary, and then it will have some nice consequence that if you have a soluble degenerated group, D is a finite number, then the number of maximal subgroups goes as a polynomial. So you ask this, there are some not just finite groups, but groups like profinite groups, other infinite groups, which I don't want to talk about. But polynomial is small again. So this basically says that soluble groups have just a few maximal subgroups in subsets. That's the content. And for more on this index and maximal subgroups or index and subgroups, you can find more in the book of Dubotsky and Siegel, which has a nice title, Subgroup Growth. Actually, it's an extremely useful book because it has windows, nothing to do with any computing system, but in there are some little chapters explaining concisely what the authors consider important about simple groups, linear groups, and others. And actually, probably this is the most useful part of the book. If you don't want, even people who don't want to work on this subject tend to look and refer to this. So there's useful information, even apart from the actual talking. So there is a little bit more on this, but why is considering the number of maximal subgroups interesting? Because it leads to random generation questions. So, for example, there are people who actually want to compute with matrix groups, permutation groups, and for this it's really good to know how many random elements need to generate a group with high probability. You pick elements somehow randomly from your group, And if you have a result that tells you that if you go long enough, then they generate, that's very helpful for algorithmic purposes, because typically these algorithms are random algorithms. So therefore, the number of random generators is a topic which interests a lot of people, more than I think the number of people interested in just counting groups. And for this, you really have to consider this function. But let's go back to this in a different way. A nice consequence of the classification, actually proved by Steinberg for groups of 3 type and Ashberg-Rurali for sporadic groups. You take any non-abelian, any finite simple group, then it can be generated by at most 2 elements. This is a very strange property. Okay, well, abelian simple groups have prime order, they can be generated by 1 element, and you may have even been subjected to prove that the alternating groups AN, no matter how large n is, can be generated by 2 elements. The point is that this persists, at most 2 elements generated. There is no indication why this should be true without the classification, but it's a very useful property. And interestingly, much more is true. Basically, there is a result first proved by Dixon for alternating groups, Cantor and Watsky for many classical groups, finished off by Lee-Mechelef, which basically says that if you take 2 random elements, then they, with high probability, they generate your simple group. So if the simple group is large enough, then the probability is close enough to 1, actually. And the proof, somehow, most of the proof is basically what? Like, okay, that's how I like to draw, for some reason, the alternating group. And then you have maximal subgroups. If 2 elements are contained in some proper subgroup, that is, 2 elements don't generate if they are contained, if they generate a proper subgroup. Then they are contained in a maximal subgroup. Okay, there are a certain number of elements contained in this maximal subgroup. Let's suppose if it's n, then it's m squared. And then there are a certain number of elements here, a certain number of pairs of elements here. And you can count them if there are not too many maximal subgroups. Eventually you see that not too many pairs are contained in them. Therefore, typically there is outside. That's the philosophy of the proof. Of course, there are a lot of technical details. Okay, so, but it sort of explains you, Dixon's proof originally was different. He didn't use the classification theorem for the alternating group. This is not in Babai's proof, where he counted more precisely and gave a better estimate. But that in some sense tells you that counting maximal subgroups gives you random generation results. And actually it's a beautiful result that you take 2 random elements from the alternating group that typically generates. It's actually, it was somehow, there's a book by a guy called Netto, written in 1890 something, and there he conjectures this. And somehow it was forgotten for a long time. And then Erdős and Turán and others investigated the properties of random elements of symmetric groups. And I think Erdős told me that they actually tried to prove this conjecture, but didn't know enough group theory. But Dixon knew about their results and he knew enough group theory, and he's a clever guy also. So he managed to prove this. Okay, and it's nice because it's completely elementary. Okay, but it has, and also it has a wide generalization for simple groups. So the simple groups have this property. We really understand how the random elements generate. Not more. You don't need more than the minimum number. Okay, it's 2. So basically, the question that I'm trying to lead up to: what about groups in general? Is there anything similar, any of this phenomenon? Or arbitrary finite groups? Okay. Okay, so this is gone. And an indication was proved by Avimam. So he basically proved that if you have a finite degenerated soluble group, then constant times d random elements, like 10 times d or 4 times, I always tend to forget, but absolute constant, let's say 10. 10 times d random elements generate with probability, okay, he loves to state 1 over e, he could stay 1/2, but people like to say 1 over e, it doesn't matter. Really. Okay, so this basically is the same phenomenon. Okay, that in simple groups, 2 was the possible minimal numbers, 2 was sufficient. And here, okay, if you have d generators, then 10 times d generate with very large probability. It's easy to see, you cannot expect more. So there's the same kind of phenomenon for soluble groups. And this is basically a 2-line application of the corollary of that homework. And that's how it was done. So that one knew about this and turned it around and found this very pleasant thing. So it basically tells that soluble groups are quite similar to simple groups. You don't need too many random generators, once you know the number of generators. So then it became a topic, of course, if you have a nice result. And you need a little bit more notation. Motivated by this result, mu of g is the minimal number k such that k random elements generate your favorite group with probability 1 over n. Again, it could be 1/2, doesn't matter. And a very nice result of Lubotsky, Datomi, and Lucchini, it's again independent, says that something like that not too many more. So dg is the number of generators. And there's a result which says that not too many more are needed for random generators. And it's a surprising sort of that you have to add only log of the order. All average just log. Log is okay, but log is even nicer, +5. Okay. But still it can be large for large groups, like products of many alternating groups of the same degree, that kind of stuff. an to the n factorial over 8 or something like that. Anyway, there are some groups where you actually need this. And I mean, obvious from this, you cannot expect a formula for this new g. I mean, it's quite clear. So the point is that there is a formula, which we could prove a few years ago. What do I mean by formula? It means that if you have your group, it has certain structure, certain normal subgroups, quotient, and you can dig up a number from this structure and concoct a really ugly expression, and it tells you mu of g exactly up to an absolute constant number. And again here, what I find is, the point is not that we could prove it with this very nice guy Andre, but that it exists. There is such a thing. Actually, we were trying to prove something different, which was sort of clear that you can get some kind of an answer, and then we worked on it for a year and a half, and we got an answer, and then eventually we realized, hey, we can say something elegant about finite groups. Just to discourage you, I will tell you the result, the actual result. So there's lots of notation. So let L be a non-abelian simple group. Then A will denote half of this non-abelian simple group. And LA, not Los Angeles, but the minimal degree of A as a transitive group. It has faithful transitive representations. Like it has 1 degree size of A, a regular representative. But you can somehow push it together, you know? Okay, so how fat is this group? This is this L of A. And I told you that you have to dig out some invariants from the structure. So we are interested in things like you take a normal subgroup, another normal subgroup, and then there will be such that this section between will be a direct product of isomorphic minimal normal subgroups. I'm trying to get, okay. So rank A of G is the maximal number R such that there is such a section, normal section, such that is the product of R minimal normal subgroups. So somehow you have these numbers and these numbers. You can even forget the meanings. And then what we proved, it appeared in 2011. It took quite a long time. We submitted it to the Annals of Mathematics. And actually, there's a funny story that a year, Andre is in Madrid, so a year after submission, we realized that we didn't submit. We were sitting in Oberhof and realized that the other, each of us expected the other to have submitted it actually. And then we were sitting like that, and then we submitted, then it just took about 2 or 3 more years to get accepted, and then to appear. So it's an old result by now, but it appeared in 2011. So the formula is something like, there is an absolute God-given constant, whichever God you prefer, beta, number of generators, plus the maximum of logarithm of rank AG, I define rank AG, and logarithm of LA. So this thing is less than mu of G, the number of random generators you need. And then there's another constant given by maybe another one, alpha times dog max, so the same expression. I just forgot to write it in O, it's the same. Maybe I just leave it. Okay, so this expression basically tells you the number of random generators. It's completely useless actually because alpha and beta are horribly large. So in fact now there are some guys, unfortunate people, students in England who try to get precise constants in this kind of results for purposes of computational group theory. So good luck to them. It's nice work. Okay, so there is an expression. And what does this mean, sort of? A consequence is, we want to, we had our earlier results about simple groups, soluble groups, Tubolsky's result. So what does this tell about simple groups? If you look at it, don't, but if you look at it, it tells you that boundedly many, not 2, but boundedly many random elements generate G is probably not 1, but 1 over epsilon. So this is a weaker version of Dixon theorem. Dixon is not weak, but it's a weak version of Dixon theorem. And similarly, you get back the results about soluble groups, Tubolsky. So all the previous results are very simple consequences. And there are some others. There were some unsolved problems about profinite groups that it solved, but somehow all this tells you that this horrible expression is the right one. And about the proof that the key step. Okay, so I actually went to Madrid because I was learning salsa and it seemed like a nice place. So I went there and I told this to Andre. And he said, okay, here's a list of salsa clubs. But you are here for a few weeks. I don't have many people to work with. So we have to work. And let's work on this problem. Before that, we tried working on something. And it didn't work out because something is something. He said, okay, let's work on this problem. And so I went to salsa clubs in Madrid. They start after midnight sometimes. So it's 12, there's nobody there. Anyway, so one is getting into this daydreamy kind of state, which is sometimes very good for mathematics. Not for writing actual proofs, but for, okay. So anyway, during this salsa visit, we managed to prove, you don't have to remember them telling you that the consequence of this homework lemma was the number of degenerated primitive soluble groups is small. And we could erase the word solid. Maybe that was the main result of these 2 weeks. And actually I wanted to erase this word for like 20 years. I didn't know how, but then I had an idea and I had a wonderful co-author who just worked like that, and we managed to erase it, and that was the key to all this. So that was the point. Okay, thank you.